Section 10.1. So chapter 10 talks about sequences and series. And here we're going to really spend some time mastering, well, 10.1 is only sequences, but the rest of chapter 10, 10.2 through 10.6 talks about the different types of sequences, series that we have, and we test for convergence or divergence. 10.7 is a section that deals with radius and interval of convergence. Where do these converge? And 10.8 through the rest of the chapter, you really take any math function that you can think of and write it as a power function, which is a series, that is. And then we test whether it converge or diverge, and so on and so forth. So, what is a sequence? A sequence is a list of numbers in a given order. A sub 1 is the first term on the sequence or on the list. A sub 2 is the second, obviously. The ordering is very, very important. A sub n is the nth term on the list. And it's extremely important because if you can find it, it generates the entire sequence. So we just want to make sure you remember some of this. The first set of problems on page 585 is really just baby steps. This is the general term. Can you tell me what the first four terms are? Well, look how it works. Wherever you see an n, you plug n in. Now, it would save you a lot of pain. Since I didn't mention yet, I was waiting until we get to the actual definition, but now I'm going to mention this n right here. This n is a whole number. To us, if we are coming up with the sequence, we always say this is a natural number. We say n could be 1, 2, 3, a natural number. But sometimes the author adds 0 when they're finding this. We're not going to disagree with that. If we're finding this, the general term ourselves, we start with 1. We can start with 0. So in that order, if I told you this is n, the next would be n plus 1, and the previous would be n minus 1. Right? Maybe I should have started a bit simpler. If I was to say we're dealing with whole numbers, can somebody tell me what's after 117? Well, obviously 118, and before that 116. What's after n? Well, whatever n is, since we're dealing with positive integers or whole numbers, n plus 1, and the one before would be n minus 1. If you make that the subscript of a, that could save you a lot of pain. You can always think of, if a sub n is the term I have right now, a sub n plus 1 is the next term, and a sub n minus 1 is the previous term. That doesn't look like a subscript. Let me fix that. And that doesn't look like a subscript. Let me fix that. So if you could do that on the long run, things will come out a lot easier, and the theory will fall into place much nicer, especially when you need theorems and remainder / error. So if I glance at this problem, say, okay, well, let's see. What are the first term? Well, a sub 1, throw a 1 in there. That is 2 plus a negative 1. That's a 1. A sub 2 would be 2 plus a negative 1 squared. Wouldn't you say that's 2 plus 1, which is 3? And a sub 3, wouldn't you say a sub 3 is 2 plus a negative 1 cubed? Isn't that a 1? How about a sub 4? 2 plus a negative 1 to the 4th. Isn't that a 3? So this sequence consists of 1, 3, 1, 3. What do you think the next? Isn't that going to be 1, 3, 1, 3 all throughout? So the key out of those for us is to get this part out. That's kind of taking 2, if you really think about it, and it's adding 1 and subtracting 1, limiting between 3 and 1. That's called oscillation. Oscillate back and forth, non-stop. If I look at number 6, if I want to list the first 4 terms, again, just getting acquainted with this, wherever you see an n, replace n by 1. That is 2 to the 1 minus 1 over 2 to the 1. That would be 1/2. If I go for a sub 2, I notice that's 2 squared minus 1 over 2 squared, 2 is 4, that's 4/3. If I go for a sub 3, that would be 2 to the 3rd minus 1 over 2 to the 3rd. That is 8 minus 1, 7/8. And if I go for a sub 4, that would be 2 to the 4th minus 1 over 2 to the 4th. That is 16 minus 1 is 15 over 16. Can you guess what a sub 5th is? Now notice what I'm getting at. If you really start playing with those, the goal is, I did mess up here, didn't I? Look at that. I figured that out from what I was about to do. The goal is to figure out a pattern if you could. Sometimes it's really easy to figure out a pattern, and sometimes it takes a lot of work. If it's arithmetic or geometric, it's simple because I know the formulas, but if it's not, I have to figure that out. Well, look at that. If you take 1 plus 2, isn't that 3? And the bottom is 1 more. If I take 3 plus 4, isn't that 7? And the bottom is 1 more. If I take 7 plus 8, isn't that 15? And the bottom is 1 more. If I add 15 plus 16, isn't that 31? And the denominator is 1 more. Again, that's not a must, but normally that's the purpose. The purpose of you seeing the pattern is to try and figure it out so you could come up with a formula, right? But what I just explained is a recursive formula. We're going to talk about that in a minute. Now, let me move to the next set of problems. And guess what they say? Recursive formulas. So what's a recursive formula? As you noticed, I had to look at the first term to figure things out. And this is where this analogy could save you a lot of work. So let's see what this says. This really says the first term on this list is a 1. So here, we have a 1. We want to find the first, given the first term or 2, recursive formula, write out the first 10 terms of the sequence. 4 or 5 will do. It doesn't have to be 10, but we're going to follow directions for this one. A sub n is a sub n divided by n plus 1. So if you think about it, to find any term, now do you see how those were related? To find any term, in this case, I'm going to take the term before it. I'm going to take the previous term and divide it by this number. This number. So, for this to work, I need the first term. Just like here when I said if you add those, well, for this to work, you need the first term. If I don't tell you what the first term is, don't you always add those? If I don't give you that, then how are you going to know what to add? So that wouldn't work. So, in this case, I want, the first term is a 1. What's the second term? If I want to look at the second term, according to the formula, that's the first term divided by, again, whatever this number is, let me match the colors. Here we go. And isn't that 1/2? Now, what's a sub 3? Well, a sub 3 is the previous term, a sub 2 divided, and whatever this is, the denominator is. So that is 1/2 over 3, that's 1 over 6. Trying to figure out a pattern if I can. Sometimes you can, most of the time you can't, especially if it's recursive. The previous term divided, again, whatever this is, that is 1 over 6 divided by 4, that's 1 over 24. Yeah. I kind of messed up, but that's okay. If you want to figure out a pattern, you shouldn't multiply. You should leave everything as is. So here I would have 1 over 2 times 3 divided by 4. That turns out to be 1 over 2 times 3 times 4. Anytime you want to figure out a pattern, I don't mind on the homework you're writing 1 over 24. It's fine with me. You want to find a sub 5. That is a sub 4 divided by 5. That is 1 over 2 times 3 times 4 divided by 5. So that is 1 over 2 times 3 times 4 times 5. And guess what? In this case, I'm able to figure out a formula. This is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. This is a sub 5. Wouldn't you say I could replace a sub n by 1 over n factorial? So what's a sub 6? 1 over 6 factorial. What's 6 factorial? It is 6 times 5 times 4 times 3 times 2 times 1. There, we figured out the pattern, which is really what we need for this. Again, just to practice, nothing more. Find the nth term. The reason I'm picking number 14 out of anything else, this is something we're going to need coming up. You notice this is an alternating sequence. Anytime you see an alternating sequence, -1 to the n. If that works, you're in good shape. If not, either you make that a +1 or a -1. Meaning, if I put a 3 in there, if I look for the third, put a 3 in there, that's -1 to the third, that's -1. A sub 1, a sub 2, a sub 3 is negative, it checks. If it didn't check, that means you're off by 1. Either you push it 1 up or 1 down, and that'll do the trick. That's something that we're going to have to do pretty soon. Alright. A sequence a sub n converges to a number L if the limit as n approaches infinity of this general sequence, general term is L. So you take a sequence, you write it as a general, you find the general term of the sequence, and if you take the limit as n approaches infinity of that general term, and that exists as a number, then you say this sequence converge or convergent. Otherwise, if the limit doesn't exist or the limit is infinity or negative infinity, you say this series is divergent. Now the notation that are used for a sequence are slightly different than the traditional. So sometimes they write this. Just the first 3 or 4 from the list, ... done. Or sometimes they only write a sub n, basically what I put up there. Or sometimes they write literally a sub n, they tell you where to start and where to end. So that's normally how we write it. And this notation, the limit as n approaches infinity, sometimes they write that as a sub n approaches L. Again, just different ways of writing those. I'm looking at Theorem 5. Theorem 5 is on page 584. It has 6 things. You can look at those. These are the 2 I need. Now, I know if you're dealing with an exponential and the base is between, the base is less than 1, then it's fine. But if you're dealing with an exponential function is a function in which the base is bigger than 0, not equal to 1. This says if the base, so kind of like exponential, if the base is not less than 1, between 0 and 1, if the base is between -1 and 1, this will be 0, something I'm going to use. And for now, when we get to section 10.6, we will deal with the ratio test and the root test. The ratio test will deal with that. Until then, we're going to quote theorem 6 every time we find that limit. These are the only two we are allowed to use out of theorem 5, I'm sorry. So